Our next speaker is my roommate and also my great friend, Josh Kasper. He grew up in the Sierra foothills and received his bachelor's in business management and later worked as a financial advisor before realizing his desire to pursue a career in the wine industry. Josh managed a boutique winery for several years where he developed a strong interest in wine production. And following his passion, he went on to work harvest at Skinner Vineyards, Gross Ventre Cellars, Farron Wines, and Arista Winery. And Josh began the Viticulture and Enology program at UC Davidson in 2019. And after graduation, he plans on working at, or he will be working at the Napa Valley Reserve in St. Helena. So with that, I'll leave it to you, Josh. Take it away.
Thank you, Stephen. So the topic I'm covering today are the factors that influence Chardonnay being predisposed to sluggish and stuck fermentations. And this is the outline for today. First is the introduction. Why is Chardonnay important? A review of sluggish and stuck fermentations, and a quick review of the macronutrient nitrogen. Key themes of the paper are Chardonnay's disposition for an imbalance of amino acids, how white fruit cultivars that are high in proline are limited by vinification procedures. Also rootstock properties and their effect on amino acid composition of the fruit, and then we'll have our conclusion. First, why should we care about Chardonnay? Chardonnay is grown in almost every major wine region around the world, from California to New Zealand. Recently surpassed Arian as the main grape. It is now the most widely planted grape globally. According to the California Crush Report, Chardonnay continues to be the largest percentage of total tonnage crushed in California for a consecutive 16 years. Before that, Concord grape juice was the main grape before Chardonnay took the one spot. And it's estimated that the crop is worth more than $445 million in California in 2020. So sluggish and stuck fermentations are a common problem, and it can lead to the proliferation of undesired wine characteristics, and spoilage results in major economic loss for wine producers. Problematic fermentations are complex interactions and are often due to a combination of factors. The common factors that lead to sluggish or stuck fermentations typically are substrate inhibition by excess sugar, ethanol toxicity, toxic substances, temperature shock during fermentation, and nutrient limitations. From my review, it appears that one of the main factors I found affecting Chardonnay fermentations involves the nutrient limitation of the macronutrient nitrogen. So the typical sluggish or stuck fermentation for Chardonnay often happens towards the end of the fermentation when the yeast is under stressful conditions, and this leaves higher than desired sugar content in the wine, usually at concentrations above 2 grams per liter. Sluggish fermentations place time constraints on tank space during harvest, and provides an environment that's more susceptible to microbiological spoilage. And it often results in time-consuming restart inoculations that can often affect quality. Also, some producers choose to over-vintage Chardonnays and hope that the extra time in barrel will allow the fermentation to slowly finish. But even if it does, this is at the cost of not being able to move the product to market. So in winemaking, nutrients like nitrogen and grape must are essential to successful alcohol fermentation. It directly influences yeast proliferation rates, kinetics, duration, and overall success of the fermentation. Ammonia and free amino acids are the major nitrogen sources that can be assimilated and used by the yeast. So some of the main amino acids found in grapes are alanine, glutamate, glutamine, serine, threonine, and valine. But the major 2 components, arginine and proline, make up the greatest proportion of a total amino acid concentration present in the grape. Percentages and their concentrations change depending on the study and the cultivar, but typically it accounts for 68 to 80% of the amino acids found in the berry. So first, we're going to take a quick look at arginine. It's a free amino acid, and it's the most abundant usable form found in the grape. Its accumulation begins pre-veration, and it's utilized after nitrogen sources like ammonia have been processed. So for arginines, yeast pathway for arginine degradations, take a quick look at oxygen is not required. And the arginine degradation is catalyzed by arginase, yielding orthanine and urea. Urea is then degraded, resulting in 2 ammonia and 2 carbon dioxide. Orthanine and the other end products of arginase reaction is degraded by glutamate, semihaldehyde, and this is the important part. The end product is more proline at the end of the pathway. So this is sent back into the must of the wine. So next we take a look at proline. Proline is a non-assimilant secondary amino acid. And under anaerobic conditions, yeasts do not use proline as a source of nitrogen. Significant proline accumulation in the berry starts post-verasion and typically continues to climb. Proline is required by the yeast cells for stress tolerance of ethanol. And one thought is if proline levels are too high, their tolerance of ethanol is to a point where they don't autolyse and contribute amino acids back into the wine. So they kind of become too resilient for their own good. Proline accumulation at high levels in the berry appears to be associated with grapevine stress, particularly heat, low moisture, and high levels of salt. Certain cultivars accumulate much higher levels of proline for reasons that are not fully understood yet. And there's also speculation that elevated levels of proline may inhibit yeast metabolism, but this is still an area of current research. So the yeast pathway of proline degradation involves proline oxidase, which requires oxygen. So that's a very important part. Under anaerobic fermentation conditions, proline cannot be utilized as a nitrogen source. Proline breakdown then occurs through proline 5-carboxylate to glutamate. So next we're going to look at Chardonnay's disposition for accumulating proline as a varietal. We're going to look at a study first done at UC Davis that examined the amino acid profile of commercial grape juices and wines. 300 juice samples of different varieties were collected from 23 different wineries in Napa and Caneros. The goal of the study was intended to supply an accurate amino acid profiles for commercial juices and wines of different varieties. And the data of the dominant amino acid juices were chosen for comparison to see if amino acid compositions reflected genetic differences among the grape varieties. And the 2 above graphs show the amino acid survey of Sauvignon Blanc and Chardonnay. The proline and arginine were the predominant amino acids. But you can see over in the Sauvignon Blanc, the level of arginine, the usable form by yeast, is much higher, and proline is moderate. In Chardonnay, proline level is almost twice as much, and arginine levels are relatively the same. On the same study, a comparison of amino acid levels of Chardonnay juice and its wine from a vineyard in Rutherford was done. The comparison of the juices showed that the majority of arginine was utilized by the yeast during fermentation, but proline was not really utilized, and the levels remained almost unchanged. So you can see the hashed line is the juice, and then the wine. And you can see all the arginine was utilized. The proline basically was untouched. Again, the same study, they compared the proline and arginine levels of Sauvignon Blanc, Chardonnay, and Cabernet Sauvignon. Again, arginine levels were almost the same for all three of them. Chardonnay had significantly more than Sauvignon Blanc. And then Cabernet Sauvignon is also a varietal that's known for proline accumulation. But being a red cultivar, there's some differences we're going to talk about next. So high levels of proline in ripe white fruit grape cultivars like Chardonnay are much more problematic than in red fruit cultivars like Cabernet Sauvignon that also have high levels of proline, but it has to deal with vinification processes and oxygen exposure. So the first study we're looking at here examined proline utilization under the presence and absence of air. So they took 3 fermenters that were air flushed and another 3 fermenters that were flushed with nitrogen. And in each set, there was a control, an amino acid addition, and a yeast food supplement juice. The study showed that proline was easiest utilized when air was blown into the fermenter's headspace. The nitrogen flush fermenters were not able to use proline, and in some cases even saw elevated proline levels. And that was from the excretion of proline, or from arginine being used and excreting proline as a byproduct. You can also see the fermentation days, the comparison there, substantially more. Also, the location of amino acids in the grape are important to consider in winemaking. One study found that the juice or pulp of the berry contains the highest concentration of proline at 50 to 80%, where the skins and seeds contain greater than 50% of all the other usable forms of nitrogen. So it becomes important depending on the vinification method. The combination of vinification procedures for Chardonnay is to first crush or add a whole cluster into the press, where it's separated from the skin and seeds and collected to tank and then racked to barrel for fermentation. This method of vinification primarily collects the juice that has the high concentration of proline and does not allow proper extraction of the nitrogen that's present in the skins and seed. White wine vinification doesn't involve cap management, so oxygen exposure is avoided out of concern of oxygenation of the wine. The combination of these practices greatly reduces the extraction and availability of nitrogen reserved in the skins of the grapes for the proliferation of fermentation, and prevents the utilization of proline due to the absence of oxygen. Red varietals that are high in proline, such as Cabernet Sauvignon, are typically crushed, destemmed, cold soaked, and fermented on skins. This allows for great extraction from the skins and seeds. Also, during fermentation, cap management is done where pump overs, punch downs are done twice a day. So oxygen exposure is great during those procedures, and that allows for the introduction of oxygen for the formation of proline dehydrogenase, which is the first enzyme that starts the pathway for the utilization of proline. So next we're going to look at how rootstocks play a part. Rootstocks are the primary method that water and essential nutrients, such as nitrogen, are uptaken by the vine. And this affects vegetative growth and reproductive growth in plants. Rootstocks differ in their many unique properties, which can affect root dynamics, nitrogen uptake, vigor, and fruit composition. Studies have also found that genetic differences of rootstocks and their properties can have an effect on the nutrition of the vine and amino acids. One study from South Australia measured the free amino acids present in the fruit of a large Chardonnay rootstock trial. Over 2 years, they found that the lowest concentration of free amino acids from Chardonnay vines were on 140 Ruggieri and 101 14 rootstocks. The highest concentrations were found on vines from their own roots, Schwartzman and K5140. They also had the highest levels of amino acids that were able to sustain fermentation completely. Other studies have also shown that 101-14 has been problematic for increased proline levels. One last case study that involved coastal California Chardonnay that was very difficult to ferment. All corrective measures were tried by the large producer, but could not correct the issue. It was found that the application of nitrogen in the vineyard over time improved the nitrogen balance in the fruit and resulted in fermentation performance. The vineyard in this case didn't show any signs of nitrogen deficiency besides the amino acid imbalance in the fruit. Nitrogen applications were added at 2 times the normal rate over the period of 3 years. Each consecutive year showed an improvement of proline-arginine ratios and improved fermentation rates, but it took 3 years of elevated nitrogen additions in the vineyard before the fermentation rates improved to match those of easy control fermentation juice. So in summary, Chardonnay as a varietal has been found to be a proline accumulating fruit with a high proline-arginine ratio. Vinification methods for white wines like Chardonnay prevent the utilization of proline as a nitrogen source, and rootstock properties and their effects on amino acid composition on the fruit can possibly mitigate or further enhance the problem of amino acid imbalance in the berries, depending on the selection. Vineyard application of nitrogen during the springtime over several years has been shown to lower proline and arginine imbalances in the berries. Lastly, possible areas of research is determining actually why some cultivars are prone to this amino acid imbalance. Continued rootstock evaluations, determining which ones would be the most useful, and advances in yeast strains that would metabolize proline in anaerobic conditions would be super beneficial. And with that, I'd like to acknowledge the Michael Bonascori Scholarship Fund, the Peter Shields and Henry Jastrow Stipend Award, Professor Block, Professor Cantu, Professor Besson, and also my fellow peers in the program for their friendship and support. With that, if anyone has any questions. Well, thank you, everybody.
Thank you both. It was very good. Thank you. Guys, we were done with the plan twos. Next week we're gonna have a plan 1 and then a PhD student. So thank you very much. See you soon. Bye-bye.
Thank you.